Hello. Today we're doing analysis, Yanofsky, we're doing analysis of algorithms, chapter 12, binary search trees. Okay, binary search trees is really, you probably most saw it already in data structures, but we're just going to do it, we're going to do it fairly quickly and get into the more nitty-gritty details. But again, we're not just doing the algorithms, or we're not just describing the data structures, we're also going to be very interested in efficiency. How much work is done? Okay. So, let's begin. First I have to tell you what a binary search tree is. Actually, first we give an example of what a binary search tree is. Okay, so it's exactly as it sounds. It's a tree, so we know what a tree is. It's binary, it only has at most 2 children, each node, and it's easy to search on. So let's just do examples. Okay, here's V. T is less than V, R is less than that, U is more than V, S is more than that. Okay? As opposed to that, V, W is more, Y is less, X is less than that, and Z is more. Okay, so here's a typical example of a binary search tree. We're going to see more examples in a second, but let's just give a formal definition. You can think of it as a heap. Let's just remember, but it's not a heap. Okay, so let's just remember the definition of what a heap was. A heap had the following property: every father is larger than both its children. Okay, here it's not. Here it's every father is larger than his right child, okay, but is less than his left child. So it goes like this: let Y be a node in a binary search tree. If X is a node in the left subtree of Y, then key of Y is less than or equal to key of X. Okay. Okay. So here I use the exact same thing. X is a node. Key of Y. Whoops. Sorry. The key of X is less than key of Y. Okay. So the left subtree is less. Okay. And now the other one is the right subtree. And then we have key, say Z, is in the right subtree. Then we have key of Y is less than or equal to key of Z. Okay, so if it's in the right, it's greater than that. Okay, great. The point is as follows, is there are a lot of things that satisfy this requirement. There are a lot of binary subtrees that satisfy this requirement. This is a nice one, but there are others also. Let me just show you some others. Okay, let me just read this. Let Y be a node in a binary search tree. If X is a node in the left subtree of Y, then key of X is less than or equal to key of Y. If Z is in the right subtree, key of Y is less than or equal to key of Z. Okay, great. Let me just show you some other subtrees with the same nodes. I'm sorry, let me just show you some other binary search trees with the same nodes. You can have T in the top, okay, and you can have S over here and R over here. You can have Y over here, U over here, V over here, Z over here, W, X. Okay, So this is also. Let me just tell you one of the tricks. The main thing that we're going to see today is we like short trees. The shorter the tree, the better. The more compact it is up on top, the better. Okay? Long trees, they're not good. Okay? And the reason is as follows, is because many times we're going to have to go to the bottom of the tree. You don't want to go to the bottom of a long tree. You want to do compactness. You want to have things compact and have that up on top. Okay? Now, just again, these two trees have the same nodes, but obviously this is shorter than this. There's an extreme case of these. Okay? And the extreme case is as follows. Okay? Here's one extreme case. R is less than S, is less than T, is less than all the way down to Z. Okay? This is, it's a tree technically, but it's a long snake. It has everything in it. And of course there's the other way also. So you can have Z less than Y, less than X, all the way to R. Okay? Again, these are longer. These two are much longer than this. We like this, we don't like this. Okay, great. The book has other examples. You have to read the book for the other examples. Okay, first algorithm that deals with such data structure. Okay, it's in the book. It's page 288. Okay, and it's in order tree walk. X, it says as follows. If X is not equal to nil, okay, then in order tree walk left of X, okay, print key of X in order tree walk right of X. Okay? It's a recursive algorithm. First do the left side, then do the center, then do the right side. So, for example, you don't necessarily have to start at the top. If you want to do this, you first do the right side, the left side. Okay. Now you're going to do the right side. Okay. Okay. So if you call the right side, so he's going to call the right side. His child is nil. His child is nil, and so we're going to have. What do you do nil? Do nothing if nil. Okay, fine. Then you're gonna, so when you called the right child, the left child of this, you actually did nothing. Great. Then you're gonna print the key. I'm sorry, when you called this one, then you're gonna print R. Okay. Then you're gonna call the left child. Left child here is gonna call this. Try to call the left child of that. Not gonna work. Print S. So first it printed R, then it's printed S. Okay. Then it's going to print the right child here, not going to work. Then it's going to go back here, print T, so RST, okay? And then it's going to print the left of this, try to print the right, nil, print U, so RSTU, and print the right. Okay, so that does this. Very good. So if we just did a walk through these things, it would print it in order, RSTU, which is exactly what we wanted. And again, we could start here, and it would do RSTU, then it would print this, then it would print this, then it would try to print this, it would fail, there would be nothing here, it has no left child, so it would print W, then it would do a right, visit all the right things here, and so it would be XYZ. Okay? So this is very nice. Question: how much work is done? And by work I mean how many print statements. Okay, that's the significant thing. How many print statements? And the answer is O of n. Okay, we're going to see that very, very interestingly. It's going to show up over and over. The amount of work done. Here are two other algorithms that show up very often. The first algorithm is called tree search. Find an element. It says as follows. X is the root of some part of the tree. In other words, it's the beginning of the tree, and I want to look down that tree, that subtree, from X as the root, down that subtree for an element whose key is K. Okay, so we do it. If X is equal to nil, in other words, if that root that you're looking at is nil, then it's not there, so stop. Otherwise, or if K is equal to K of X, in other words, if you found what you're looking for, okay, then return X. If K is less than K of X, okay, so if it's not there or it's what you look at, then return X. In other words, this is the element that you have. That's the thing. Okay. Next, if K is less than K of X, in other words, if it's on the right side, then return tree search left of X. Look at the left subtree, and again keep the K. In other words, you're searching for K. Else return tree search right. Otherwise, if it's not equal and it's not less than, it must be more than. So look at the right subtree. Okay. This is the reason why binary subtrees were invented. Exactly this search algorithm, because it's quick to do. This is one of the first algorithms you'll learn in computer programming, namely the binary search algorithm. Okay? When you're looking for something, don't look brute force search, try every single possibility. Split the list in half, look to the left. Should you now decide, should you look to the left or should you look to the right? Anyways, question. How much work is done for this algorithm? Okay. Oh, I'm sorry. Let's do a typical example. Let's say you're looking for U. Okay. So you go here. U is less than V. So U is not here. U is less than V. So you go here. Okay. Okay. Now you're looking for U. U is more than T. So you go here. Now you found it. Okay. Great. Let's say you're looking for P, the letter P. So P is less than V, so you go here. P is less than V, so you go here. P is less than R. P is less than T, so you go here. P is less than R, so you go here. Now, the subtree you're looking at is nil. Okay, what do we do when it's nil? We just return X. So what are you going to return? Nil. It's not here. Okay. Let's just look for U.5. U.5 is somewhere between U and V. So U.5 is less than V. U.5 is more than T. U.5 is more than U. He has two children. Both of them are nil. Okay, so we're going to come here where U.5 should be. It's not there. It's going to return nil. Okay, great. Question, how much work should be done? Okay, and if you think about it, you'll probably say, oh, log n. That's the whole purpose of a binary search algorithm. It does a giant search in log of n time. Okay, but it's not log of n. Okay, it's not log of n for a very simple reason. Okay, because the tree might not be perfect. The tree might not be so crunched up and short. Okay, the tree could be a little bit long. For example, that tree that we had where we started at R, and we go to S, then we go to T, Z, okay, if we did this algorithm, then if we did this algorithm on this tree, then we'd have all n elements. Okay, so the answer is not log of n. That's the wrong, I'm sorry, the answer is not log of n, okay, but how much work is done? And the answer is as follows, and I'm going to see this over and over. How much work is done? Order of H. The order of H. Okay? H is the height of the tree, how high the tree is. So it doesn't depend on how many nodes you're looking through. It depends on how well how short and good your trees are. And we're going to see a very large theme here is that we should always have trees to be as short as possible. Okay, great. Here's another algorithm, tree minimum of x. What's the minimum? X is an element of the tree. In that entire subtree, what's the minimum? Okay, and the answer is, well, left of x is not equal to nil, x is equal to left of x. So try here, let's try here. What's the minimum here? This is not nil, so go here. This is not nil, so go here. This is not nil, so go here. This is nil, so we stop here, okay, and we return this, r. R is the smallest element of the tree. Okay? You always go to the less, less, until you can't go. Okay? By the way, that tree that I just erased, okay, from RS all the way down to Z, what's the minimum here? Well, you try to go to the left here, you can't, so R is the minimum. Okay, great. Well, that's the easy part, that's the easy one. How about this? Z, Y, X, all the way to R. Here, you're going to have to go all the way down. This shows you, by the way, what is the order of this, well, how much work is done over here. Okay? Again, you have the urge to say the height of the tree, okay, because you're going to the shortest thing, but it's not true. It's not the height of the tree. Okay? Here, I mean, yes, it is the height of the tree. You'd like to say log of n. It's not log of n. It's the height of the tree. So this is also O of h, the height of the tree. And here, that height of the tree would be n. We don't like this. We want log of n. Log of n is better. So the shorter the tree is, the closer it is to log of n. You like that. Okay, great. Let's do another algorithm. Okay. I'm sorry, this algorithm. Okay. And the other algorithm is as follows. These are cute little algorithms. They get more and more complicated as they go along, but it's totally understandable. Okay, this algorithm is called tree successor. It goes as follows. Give the algorithm a node, tell me who's the successor of the tree. Okay, let's do it quickly. Okay, so this is the algorithm for tree successor. It goes as follows. You give the algorithm x and you want to know what's the next element. So if right of x is not equal to nil, in other words, successor is going to be more than x. So you look more than it. Well, let's look at the successor of v. Okay, you're going to look more. So if right of x is not nil, in other words, it has a right child, then return tree minimum of right of x. Okay, then you look at the right side and you look what's the minimum here. And the answer is w is the minimum here. Okay, everything else is more than it. Okay, so we have to understand what's the successor. The successor of an element is greater than it. Okay, if you have a room full of people and you pick out one person, you want to know who's the one person older than that person. Well, the successor in older people, and the answer is as follows. The successor is older than that person, but he's the youngest of those older than them. Okay? Okay? So the successor of a thing is on the right hand, it's older, but he's the youngest of the older people. That's the successor. Okay? Now, it gets interesting when this fails, when right of x is equal to nil. For example, let's do this. Okay? The successor of r is very simple. Okay? You look to the right and you look who the minimum of it. The minimum of this little tree is s. Okay? It's one tree. So the minimum is s by itself. So the successor of r is s. Okay? But it gets more interesting when I ask you what's the successor of s. Let's see why. Because his right is nil. So we can't do this. and so we have to go here. Now what we have to do is we have to climb the tree. We have to climb the tree looking for the successor. And the way we do it is as follows. As always with data structures, you need two hands to teach data structures because you always have to keep track of who the parent is. So here's what you do. Okay, S is, this is X, and you look at the parent of X. That's what P stands for, parent of X. So he's the parent. And look what it says. While Y is not nil, Y is equal to R, Y is not, and X is equal to right of X, Y. So let's go through this. Here is X, here is Y, and let's see what it says. X is equal to the right of X, of Y. So that's true. Okay? Then here's what you do. X is equal to Y, so X is no longer here, X is here, and Y is equal to parent of Y. So this goes here, and this is over here. Okay? So what we just did was, we did this. We climbed the tree. We climbed the tree by this going here, and this going here. Now let's go through this. While y is not equal to nil, no, y is equal to t. It's not equal to nil. And x is equal to right of y. X is equal to right of y. No, x is equal to left of y. This fails. X is equal to left of y. Okay, so conclusion, we don't do this anymore. We go here and return y. Okay, y is t. The successor of s is t. So that works. Okay. Okay, so basically we're doing it as follows. This part is easy. Well, who's the successor of y? He's the person more than it, right of it, the minimum of the person right of it. Okay, that's the easy part. But if your tree is structured so that you don't have anybody to the right, then what you have to do is you have to look who is more than your tree, and the answer is you've got to go up to the tree. But sometimes going up the tree is a parent, and the parent is less than it. Okay? If your parent is on the left, then R is less than S. Okay? So what do you have to do? Well, you have to find the first ancestor that's to the right, that's greater than it. Okay? That's the key point. You have to find the first ancestor that's greater than it. Let's go here. U has no child on the right, so you can't do that. You have to do the second part instead. Okay? And what you have to do is climb the tree. T is not, because T is less, but the first ancestor that's more, you do that. Okay, so V is the successor of U. Sounds very good. Okay? X, the successor of X is Y. The successor of Y is Z. The successor of Z, let's try to do the successor of Z. Now, that's an interesting one. Okay? He has nothing more than it. Okay, so what you have to do is you have to climb the tree. Okay? All of the climbing is always you're climbing to the left, which means they're less, not interested in that. Not interested in that. The parent of V is nil. Okay? So, what do you do then? Well, then you stop right here and you return y. Because it is equal to nil, so the parent of V is nil. Okay? The root has no tree, no parents. Okay? The parent of V is nil. When the parent of V is nil, you fall out of this and you return y. You return the successor of Z is nil. So that's a very nice, pretty algorithm. Okay. Question, how much work is done? Well, if you think about it, you're doing one of two things. Either you're climbing down the tree to the minimum, okay, well, then it's O of H. Or you're climbing up the tree, and the worst possibility is you start from the bottom of the tree and you climb all the way to the top of the tree, and that's O of H. Okay, so you're either going to do O of H here or O of H here. Okay, and so the algorithm is O of H, the order of the height of the tree. Great. I just want to say we did minimum because we're going to do successor. Okay, but you can also do tree maximum, okay, find the maximum element of the tree, and then you could do tree predecessor. This is one of the homework problems. What's the tree predecessor? The tree predecessor is as follows. The tree predecessor is as follows. What's the definition of a predecessor? Okay, it's, in other words, the one right before it. And the answer is as follows. Look at the set of all the things less than it. Okay, a predecessor of x is less than x, but it's the maximum of those things less than x. Think about it in terms of age. I'm looking for somebody who is my predecessor in an age. So I look at all the people that are younger than me, okay, and I look at the oldest person younger than me. That's the predecessor. Okay, so that's another way of doing things. Okay, great. So that takes care of successor. Very nice. And now we're going to do tree insert. Don't want to waste your time. Okay, so this is insert. So one of the things you have a binary search tree, you want to insert a new element. So this is something we're going to do. The algorithm's on page 294. Okay, and it goes as follows. Tree insert. You give it capital T. Capital T is the tree. And you give Z an element that you want to insert. Now, the element has a key. You have to insert it in the right place. Okay, so here's what you do. Okay, you start off beforehand. By the way, I changed this. This is a different thing. I wanted another example which had, before we had every single letter from R to Z, I wanted another example where we had other things missing so that we can put it in. Okay, so you start off as follows. Y is equal to nil. Beforehand, when we were looking for the successor, we had to climb the tree. Now what we have to do is we have to climb, beforehand we were climbing up the tree. Now we're going to have to climb down. We're going to have to climb down from the root till the place where we're supposed to put the tree. We're supposed to put the new node. So we have to do that. Okay, great. So it goes as follows. Y is equal to nil. Sorry for the noise. Y is equal to nil. That is the father of the root is nil. And what we're going to do is we're going to climb down to the right place. So watch what happens. X is equal to root of t. So you're given the tree, here's the root of it. Okay, and so you have this thing. So we might as well write it. This is Y and this is X. Okay. Let's just, for the hell of it, say that we're trying to include D. We're looking to put in D. So let's see where we should put in D. So again, Y is the father of the root, and X is the root. While X is not nil, we do the following. And this is the climbing down of the tree. Okay? We do the following. Y is equal to X, so we come down here, and then question, should we go this way or should we go this way? Is the key of Z less than the key of X? Here's X, M. We want to include in D, we want to include in a node that has D in it as the key. So question, is the key of Z, that's D, is D less than X, M? Yes or no? And the answer is, if it's less, then the way we do this is, again, Y went down here, X goes here. Then X is equal to left of X. Very good. Okay, now we try it again. Okay, while X is not nil, F is not nil, then we do the following. Okay, question, is D, I'm sorry, so we bring Y down here, so now, oh, I'm sorry, so with what we did was, Y became this, and then we saw which way should we go, which way is D, which way should we go this way or this way, and so we saw that we should go this way. So now X is here. Great, now we do it again. Okay, so we bring down Y is over here, that's here, so Y is no longer there, Y is here, and now we go, which way is D? Is it this way or this way? Remember, this has a child nil. Okay, this way or this way. Anyways, D is less than F. Okay, so we go this way. So now X is here. Okay, look what it says. While X is not equal to nil, we stop. Okay, we now have the right place of where to put it. Okay, so look what it says. The parent of z is y. So now we have to do this stuff which we did in, what's it called? In data structures. We have to connect these things. So the parent of d is y. That's the parent. Okay, great. But now we have a question. He's going to be the parent, he's going to be the child, but do we connect the child on this side or on this side? Okay, stop. We have to worry about something. If y is equal to nil, when can y equal nil? The only time y was nil was up here. Okay, well, if y is nil, then just look at this. You see this tree over here? You don't see this tree over here. If y is nil, the only possibility that y is nil is if the tree is empty. So if you have an empty tree, if y is nil, then you want to put z in. You're trying to insert z. So here's what your tree looks like. That's it. So if y is equal to nil, then root of t is equal to z. You want to put it into the empty tree. So we're going to write this empty tree. It was empty, and now we have z in it. Okay, so that's just a little side case. The book is extremely exact. Okay, you don't think of these things, but it's extremely exact. Great. Otherwise, question: F is the father of D. Does it belong on this side or does it belong on this side? And the answer is, if key of Z is less than key of Y, so here's Y, okay, and here's Z, your new thing. If key, then left of Y, the left child is equal to Z. Otherwise, the right child. So question, D. So should D go here or should D go there? Well, the answer is it goes there. Okay, and so we can redraw this as follows. Put it in very nicely as follows. Here's D. Okay, parent of D is F, etc., etc. Let's do another example. Let's say I want to include H. So here's what I do. I'm going to erase our previous climbing down the tree, and let's do that. Ready? We want to put in H. So let's see. H. So M is, so we're going to start off like this. M is, and here's Y, here's X. We're going to climb down. Here's Y, and here's X. H is less than M, so we go here. So here's X. Okay, and now we do it again. A, B, C, D, E, F, G. Next. Okay. We do this again, y is equal to x, so this goes goodbye, this goes here. And should we go to the left or the right, we're looking to put in h. Z is now h, so h is more than this, so this becomes x. Okay, and we keep on climbing down. We climb again. So, question, let's do this again. X is not equal to nil, so we do this again. Y is equal to 8. So y was here, now y goes here. If key of Z is H less than key of X, yes it is, so it goes this way. So this is now X, and this is Y. Okay, so here's Y of X. Okay, but now this is now nil. Okay, and we're trying to put in H, so what do? Okay, the parent of Z is equal to Y, so this goes here. He's the parent, and the child, it's not a thing. Okay, but here now we have a good point. G has two children, both of them are nil. So does it go to the left or does it go to the right? And the answer is H is G, A, B, C, D, F, G, H is more, and so it goes like this. Okay, so it goes to the right. So let's erase this and put it in its right place. Okay, what it says is, here is H, the parent of H is Y, okay, I shouldn't have written X over there, and it's the right child, not the left child, okay, J, K, okay, if we did K, we'd be climbing, let's put in the letter K, we climb down, H, I, we climb down, and we put in k over here. HIJK, great. Okay, and V. I want to put in V. I specifically want V because it looks like V is packed over here. Where are you going to put V? V is, okay. And so let's do the same thing. We're going to climb down. Here we're climbing down. So start off root, the father of the root, climb down, this goes down, this goes here. Great. V is more than U. V is more than U, so this goes here and this goes here. V is less than W, so this goes here and this goes this way. And so we're going to put in V over here. Okay. Just for the hell of it, let's put in U.5. So here's a new thing, U.5. That's a new letter, somewhere between U and V, halfway between U and V. So let's climb down. We climb down as follows. Here's the father of the root. Go down. U.5 is more than M, so we go this way. U.5 is more than U, so we go down, and then this goes this way. U.5 is less than W, so we go this way. Okay, and now we go, which way should it go? Anyways, answer is, it goes here. Here is U.5. Okay, great. So this is a nice little algorithm. It works very nicely. Question, what's the worst that can happen? The worst that can happen is you can start at the root and you climb down, okay, and you put your thing on the lowest, you put your new Z, the thing you're inserting, on the lowest part of the tree. Well, how much work is done? Answer, from the top to the bottom is, how many times do you have to do a comparison? From the top to the bottom, you have to do O of H. And again, hopefully your H is small, but we'll see. Okay, great. Now, for the most interesting and the hardest part of this chapter, it's an easy chapter mostly, but the most interesting and the hardest part is tree delete. Tree delete. We want to take a node out, okay? And I'd like to show you what happens. It's also going to be O of H, but it's a very nice thing. Okay, there are basically three possibilities of what can happen. Okay, one possibility is you have a giant tree, okay, and you have a node in there, and that's Z. That's you want to take that out. Another possibility is you have a Z, but he has a child. Okay. Another possibility is you have Z and you have two children. I have more than two children, as you can hear very well. Okay? A loud group. Anyways, so you have three possibilities. Okay, and actually the third one is going to match up, be more interesting. Okay, there are three possibilities of what can happen. There could be, he can have no children. If he has no children, it's very simple of what you do. You just eliminate him. Nothing to talk about, nothing to worry about. Okay? Another thing that could happen is he could have one child. Now, having one child, there's two possibilities of having one child. You could either have one child over here or one child over there. Either way, it's not hard. I'm going to call one child, let's say Y. Either way, it's not hard. What do? Very simple. You chop out Z, and you make this the child of that. Okay? Same thing here. You chop out Z, and just make, he moves up into his father's place. Not hard at all. No problem. Okay? So what you're going to have is, this is P of Z. Okay? And so you're going to have the parent of Z is Y. Okay? Great. No problem whatsoever. Okay. The more interesting case is here, when you have two children. Okay, so let's think about it for a second. If you have two children, who's going to be who's going to take over for you? Okay? In this two children case, there are two types of them. Okay? One is as follows. You have two children. Okay? This is the easier case. Okay? Let me just explain to you why this is the easier case. Here's what you did. When you had no children, you just took Z, just was deleted, and that's it. When you had one child, what you did was you replaced Z with one of those children. Okay, which child do you replace? Well, either the left one or the right one. Great. When you have two children, here's what you do. You replace it with, you take out Z and you replace it with its successor. Okay? You look at the successor of it. Now, there's two places that it can be, the successor. Okay? One is, the successor can be right here. Here's Z, here's the successor of Z. Now, how do you become the successor? Well, you're the minimum of this guy. So you're the minimum of this guy. So you're nil. So, again, if your child's left child is nil, that means he's the successor. He's the one person, he's the one card after it. Okay? Well, then, it's very simple. How do you delete Z? Extremely simple. Here's what you do. You cross out Z, and this whole subtree moves up to there. Okay? Now, why do you do that? Well, notice he is not a successor. He is younger. He is the successor. He is older, so he can fit in there, and his child will be this guy. Okay? The successor, or the one who takes over Z, moves over here, and he will still be less than him. So in this case, let's say we'll call this little t, so this becomes little t, and this whole subtree just moves over. Okay? That's the easy case. The harder case is a little bit more different. Okay? And the idea is as follows. You have Z, he has two children. You want to know you're going to chop out Z. That's very good. That's easy part. The easy part is chopping out Z. Okay, but who should succeed him? Who should go in his place? Answer, his successor. So we're going to call his successor, we'll call it S for successor. There's something wrong here. S for successor. Okay? Okay, but the successor can be very far away. Okay, that's what we saw with the successor algorithm. Usually, not usually, many times the successor is to the smallest of the right, the greater than it, but the smallest of it. But as you saw, sometimes you can climb up, sometimes you can go here or there. Okay, so what happens here is as follows. You get rid of Z, and you replace Z by its successor. But then you have to worry because he seems to have more children. So you have to worry about that. And the algorithm, we're going to do that. Okay? It's a little bit technical. We're not going to go through it all. It's in the book. It's straightforward. The book also has some excellent pictures about this, showing it. But the hard part is when you have a successor, but he's far away, and how do you put them in? Okay, so that takes care of that. So let's go through the algorithm. There's a little previous algorithm before we do that, which is very nice because one of the things we saw was we take a whole thing with the subtree included and include it someplace. Okay, so we need what's called the transplant algorithm. Okay, and we're going to do that in 1 second. Okay, and it goes as follows. Okay, so the tree delete algorithm is two parts of it. One is transplant. Okay, and transplant is very simple. You have a tree, you have U, he's a node in your tree, you have V, you have a node in your tree. Okay, and what you want to do is you want to take out U and its entire subtree. Okay, so you have this tree. Okay, you have U and a lot of other things, and then you have V and a lot of other things. Okay, and both of these could be large subtrees. Okay, that's a U, not a Y. That's a U. And so what you want to do is the U goes out and just delete it. Goodbye. And the V goes in its place. Okay, so the entire U goes out and V goes in its place. Okay, V and all its children go in its place. So let's just go through it. If U dot parent is equal to nil, okay, how could that be? In other words, this thing that I'm trying to get rid of is parent is nil. Parent is nil means it's the root. So here's what you do. Then T dot root is equal to V. Then fine, get rid of it and just make the root of the tree now to be the V. Okay, so if this is the only thing in the tree, get rid of it and make this the only thing in the tree. That's very simple. Okay, else if U is equal to U dot P dot left. Okay, so we're using modern notation. Let's just see what this means. That means if U has some parent, okay, two possibilities. We're going to call this U dot P, because he's the parent. Okay, so one possibility is here's U, and here's U dot parent, and here's U, and here's U dot parent. Okay, so again, U is a node on the thing. Question, is he a left child or is he a right child? Okay, so look what it says. If U is equal to U dot P dot left, that's this case. Here's U dot P, U dot P. U dot P dot left is over here, so it's in this case. If U is equal to U dot P, so that's this case, then U dot parent dot left, then chop this off, is equal to V. So he gets out, and he is now there. Else, U dot P is equal to right. Okay, so let's do this. Here, U is not equal to U dot P dot left. It's U dot P dot right. Well, in that case, we're going to also get rid of U, but we're going to make V, and it's going to go in over here, on the right hand or on the left. Exactly where U is, that's where V is going to go. If V is not equal to nil, let's say you're trying to put in the nil thing. So if it's not equal to nil, then look what you do. V dot parent is equal to U dot R. So here's where here's the main thing. The question is, do you put it into the right or do you put it into the left of U dot parent? Okay, but one thing we can say is that V dot parent is U dot P. So whichever it is, that's the way we do it. So we're going to put it either this way or this way. Okay, the left or the right, that's and the parent of the new V, again, U is out, and we're only left with that. So basically, we're just attaching V to the right place. But as you know, with data structures, you have to do two different things. You have to attach U to its parent. You have to attach the parent to U. Okay, that takes care of that. This looks a little messy, and so we're going to erase it because it looks scary. Okay, and also we need room for the next part. Okay, the next part is the main delete thing. Okay, it's the main algorithm delete. It's page 298. Let me read to you. Tree delete, again, you can look at it in the book. The book does it exactly like this. Tree delete, T.Z. I have a tree, I have a node Z that I want to get rid of. Okay, and there are a few possibilities that we have to deal with. Okay, one, if Z dot left is equal to nil, that means it's missing a child. Okay, so it has one, it's a comment, one left child. Okay, so it has only one left child. Z has only one left child. Then look what you do. Look at the tree, take Z, get rid of Z, and who should you put instead of it? Z dot right. And this is what we said. If you have only one child, I'm sorry, if this is Z, and he does not have, Okay? He does not have a left child, then what you should do is take his right child and put it in his place. Okay? Cross out Z and put the right child in his place. Okay? We do not need this anymore because we know how transplant works. Okay. But by the way, there's another way that you would do this also. When would you do this line also? Another thing that you would do is as follows. What happens if Z also has no right child? Then this would still be satisfied, and look what would happen. Transplant T, you're in this tree, in the tree Z, T, you take element Z and you put it in its right child. Who's his right child here? Nil. So we just cross it out and put nil into there. Okay, so this case happens when there's one left child or 0 children. Great. Great. Okay, great. How about this? Else if, that means if this is not true, then we do the following. Else if z.right is equal to nil. So let's just do this again. Okay, you have z and the right is nil. Okay, well, that is very simple. Now, it could be that the left is nil too, but if the left is nil, you wouldn't have gotten here because you would have done this already. Okay, so you would have done it over there. So fine. So here's what you do. T.z, T is your tree, Z is the node that you're getting rid of. Okay, put it in here, Z.left. So this goes in here. Finish. Okay, great. So those were the two easy case. So we have comment, one right child. Those are the two easy cases. Okay, so we dealt with 0 children or 1 children. Now we're going to deal with 2 children. Okay, and it goes as follows. Else y is equal to tree minimum of z right. Okay, what's that? Tree minimum of z right. So here's z. That's the one you're getting rid of. The minimum of the right-hand tree. So here's z. He has a right child. I'm not saying he doesn't have a left child. He could very much have a left child, but he has a right child. Okay, okay. And so we're going to write this as z.right. Okay, and there's a whole tree over here. I'm not getting into it, but one of those guys is y. Okay, and look what we do. y.p if if y.p is not z, what does that mean? Well, that means his parent is far away. Okay, I'm sorry. So let me just show you when this doesn't happen. Okay, if this is nil, okay, then the tree minimum of z.right is here. So in this case, this will be y. Okay, so if y.p is not z, okay, so here y.p is equal to z. Here it's close. So this says if y.p is far away. So let's forget about this for a second. Let's forget about this for a second. Let's just do this. What happens here? He has a whole tree, but it's all from the right child. From the right child, his left is nil. So what happens? So here's the guy that we're going to move in, and here's what it says. Take the tree. Here's your z guy. Z is going out. Okay. Again, by the way, z could have many children over here. We're not interested in that. Okay. We're just looking at its successor. You're replacing z by his successor. If his successor is right there, then that's very simple. Here's what you do. Take z, cross it out, put in y. Take this whole tree, push it in. like that, transplant. Okay, and then you have to worry about the following. Y dot left, okay, so here's my new Y, so we're going to cross this out, okay, and we're going to put in Y, here's Y, okay, Y dot left is equal to Z dot left, so attach him, and you can very well attach him because he's the successor, he's less, okay, he's less than Z, he's the successor of Z, and so he is less than that, okay, and then finally, Y dot left dot P, this whole thing, Y goes along with it, this whole thing, and then Y dot left dot parent is equal to Y. So attach it correctly like that. Okay, that takes care of that. Great, that's the easy case. Okay, the hard case is as follows. Let's just do this again. You have Z, he has a child, okay, and he has a lot of, so this is Z dot right, okay, and he has a lot of other children, and the successor is far away. Okay, now I have to worry about the successor being far away. One thing I can tell you is that the successor's left child is nil. Okay, I'll tell you why. Because what is the definition of a successor? It's the minimum of a certain element. Well, if he had a left child, I could have taken that minimum. So he doesn't have a left child, but he does have a right child. He can have a right child. He does have a right child. So here, what we have to do is we have to fix the successor. So again, eventually, what we're going to do is we're going to cross out Z and put Y in there. Okay? And we're going to have no problem with this. Since he's the successor, we're going to attach that to there. That's fine. Okay? But we have a problem with him. Why do we have a problem with him? Because he already has, I want to attach him here. So here, look what it says. Okay, this is the way we fix the successor. Transplant. Take the tree, take Y, okay, that's Y, okay, and move the right into them. Move Y dot right, here's Y dot right, into it. Okay, so we go here. He goes in there. And by the way, he's got a lot of things in there, so we're transplanting. Okay, Y dot right is equal to Z dot right. Now, make his child, we take out Y, so we move him into there. Now we take Y and we make his right child to be this. So that's connecting Z dot right. Great. And then finally, Y dot right dot parent, okay, is equal to Y. So we attach these both ways. The parent is attached to the child is attached to the parent. Okay, this takes thought. This takes thought. The book has lots of nice pictures, but it makes sense. Let's just go through it a little bit easy. Review. You ready? If you have 0 or 1 child, just put it in the right place. If you have just 1 child on the right, then put it in the right place. If you have 2 children, then there's 2 possibilities. So you're going to replace Z, the thing you're getting rid of, you're going to replace it with tree minimum of that, which is basically the successor. The successor could be far away this way or far away that way. It doesn't matter. Okay, if it's far away, we have to worry about the successor's successor. Okay, and so that's what this is all about. But either way, we take the tree, we take Z, goes out, you're deleting it, and you replace it with Y, the successor of Z. And you have to worry about this. Okay, so that's the end of chapter 12 that we're going to do. I just always like to tell you, we're now going to skip a few sections, chapters, and so I'd like to tell you what's in it that we're skipping so that you can take a look at it and you know that it exists. So first of all, I want to tell you about section 12.4. Okay, it's called randomly built trees. It's about randomly built trees. Oh, I'm sorry. We didn't talk about efficiency of this algorithm. Efficiency is very simple. Okay? If you think about it, all we do is equal, transplant, transplant, transplant. Transplant has efficiency O of 1. You just move this here. There's no if statements. There's no recursion. There's no nothing. Okay, you're just transplanting, so that's not far. Okay, the only time where you had any type of recursion over here is exactly here, tree minimum. Okay, when you're going to find your successor, you might have to go from the top of the tree to the bottom of the tree. Conclusion, this algorithm is O of H. Okay, everything else is O of 1. And so that's the only hard part. Okay, great. Like we said, the hard part of this tree, of binary search trees is it might be a long time. It might be that the tree is not well structured. In other words, the tree might be a long snake. We don't like long snakes. We like short trees. Okay, so we're not responsible for this section, but it is an interesting point. The idea is as follows. Let's say I decided I wanted to build a dictionary. You can put a dictionary into a binary search tree. That's what you should really do. Now, if you think about it, the way you should do your dictionary is you should start with M and have M is the middle letter, and you have from A to M on one side, from M to Z on the other side, and you keep on doing it like that, and you have your tree very, very short. Okay, what's a bad thing that could happen? Well, I can take my dictionary and I can put in the things from A, the things from B, the things from C, the things from D, all the way down to Z. Well, in that case, I'll have my tree very long. Don't want that. Okay? You can also do it in reverse. Put your things in a dictionary like that. You'd get also a long snake. So here's something that will work. You ready? Randomly build your dictionary. In other words, randomly build your binary tree. Throw onto your tree something from A to Z. Then randomly pick a thing and insert it on the tree. Then randomly pick another element and insert it on the tree. And then randomly pick another element and insert it on the tree. Okay? Now, in that case, the book goes and shows that in general, if you do this randomly, you're probably, whatever the hell that means, probably going to get a tree that's log n, short trees. That's a good thing. Okay, so if you randomly throw things onto the tree, instead of doing it systematically from the beginning to the end, or from the end to the beginning, you're going to get a good short tree, which is what we want. Okay, so that's section randomly built tree. By the way, this is another example of something we saw last time about what we skipped in chapter 5, that sometimes when you do things randomly, you get better results than when you do them exactly or deterministically. Okay, so that's an interesting thing. Let me just tell you other things that we're skipping. Chapter 13 is a very interesting chapter, and it's used all the time, and it's used in the real world, so it's not an abstract thing. It's called red-black trees. And what they are is binary search trees, but each node is either red or black. And what we do is, when can bad things happen? Well, when we insert or when we delete, a bad thing can happen. Namely, we can delete a lot of elements and make the tree into a long snake. Don't like that. Or we can add a lot of elements, but the way we add them is they become a long snake. Again, the whole purpose of chapter 13 and section 12.4 is to keep our trees short and stout. Okay, so chapter 13 is about adding a certain property to every node. You have red and black, and the purpose is as follows, is when you add or delete, what you have to do is you have to adjust the nodes so that they stay somehow level or balanced. And what this extra information, this extra red or this extra black does is it keeps it very, very level. So that's a very cool thing to do. Okay, red-black trees. Okay, and chapter 14, again, we're not doing chapter 14, but it's interesting. It's called augmenting data structures. So here we have a very nice binary search tree. It works very well. But you know what? A lot of times you have some extra information you want to keep on your trees. Okay, extra information that you want to keep track of. And so you want to keep You want to know how to do that. And chapter 14 is a very short chapter, and it tells you how to make sure that you keep your binary search trees well, etc., with this extra information. Okay, so that takes care of that. Next time, we start chapter 15. Chapter 15 and chapter 16 are two paradigms of programming. Chapter 15 is dynamical programming. We'll see that helps, it shows up as much as recursion, and you'll see why. So it's just as important as recursion. Okay? And chapter 16 is called greedy algorithms, and that's another way. The rest of the book is, okay, chapter 1 through 4, we had the mathematical background. Chapter 5 through 9, we were doing all the sorting and searching. Okay? These chapters that we're skipping, chapter 12, 10, 11, 12, 13, 14, those are all data structures, which you saw already. We just went through this very quickly to do it quickly. Chapter 15 and 16 are going to be these programming paradigms, and the rest of the book is using all these tools to do any type of algorithm whatsoever. Have a great day.